Hey there, welcome to another video. In the last video, I showed you how to convert between polar coordinates and rectangular coordinates of a point. Same point, different representations. In this video, I'm going to teach you how to go between rectangular representation or rectangular coordinates of a point into polar. So we need to be able to go both ways. Last video was really straightforward. Not easy because it was different, but really straightforward because everything about changing between polar and rectangular representations of points works just fine. There's never an ambiguity of where you are at in whatever quadrant your angle resides for polar, and therefore there's never an ambiguity on what point you get for rectangular. However, in reverse there is. You see, here's the thing. When we did all this work last time, we said, hey, because we have a right triangle, because theta can represent some sort of an angle in polar coordinates where your point is, we can convert between them nicely because we have sine of theta equals y over x or y over r, so y is r sine theta. Cosine theta is x over r, so x is r cosine theta. And this is how we changed from a polar coordinate into a rectangular coordinate for any point that we had. Very, very nicely. However, there was two other things I gave you, I hope you remember, that the Pythagorean theorem says x squared plus y squared equals r squared, or r is square root of x squared plus y squared. This will let you change from rectangular coordinates, x and y, into polar. Oh, that's a radius. That's our r. That's what the r meant. Also, because tangent of theta is y over x, well, theta would be tangent inverse of y over x. This is what lets you change from rectangular into finding an angle. And that's exactly what polar does. Polar gives you an r and a theta, a radius and an angle, to tell you exactly where this point is in a slightly different way, a very different way, than x and y, than a rectangular coordinate system. These two are how we change from rectangular to polar. But there is one thing that you got to watch out for, and it's your angle. You see, when we do this, when we find this angle from tan inverse, we have to remember what tan inverse does. Tangent inverse only works from negative pi over 2 to pi over 2. So a couple things can happen here. Firstly, because tangent inverse only works from negative pi over 2 to pi over 2, if you have an angle in quadrants 4 or 1, if your point is in 4 or 1, you are set. Tangent inverse will work perfectly. Don't change a thing. So if your rectangular represented point is in quadrants 4 or 1, just do tangent inverse and you are basically done. One caveat to that. However, if your point is in quadrants 2 or 3, tangent inverse will not give you that angle. It will only give you angles from 4 to 1. That's what tangent inverse does. It's only defined for negative pi over 2 to pi over 2, so it can't even give you angles in quadrants 2 or 3, from pi over 2 to 3 pi over 2. So here's what to do. If you have a point in quadrants 2 or 3, and your angle's only going to be given in quadrants 4 or 1, just add pi. So we're going to be plotting our points. We'll determine our quadrants just like we did in the last video, but we're going to understand that if our point is in quadrants 2 or 3, our angle that's given to us from quadrants 4 or 1, we just have to add pi to get there. It's going to work out just fine. I also said there's one more caveat. If you have a point in quadrant 4, your tangent inverse will give you at a negative angle. It's how it works, from negative pi over 2 to pi over 2. It's going to give you a negative angle. If you don't want the negative angle, if you have to have a positive, just add 2 pi. And it'll bring you right back to quadrant 4, but it'll be a positive angle. So with that's basically everything we're going to be doing. That's a whole entire lesson. We just need to practice right now. So I'm going to walk you through exactly how to do these examples. Change between rectangular coordinates and polar coordinates for a point. There's really not a lot to it beside this, beside understanding exactly what angle is being given to you based on our definition of tangent inverse. So as we go through, I'll be explaining everything again that I've just done, but because this was not really super concrete because we have an example, it'll make more sense as we go. So let's get right to it. The first thing we're going to do is identify what sort of a representation we have. Do we have rectangular or do we have polar? Sometimes it's very difficult to tell, especially with something like 3, 0. That could easily represent polar coordinates with an r of 3 and an angle of 0. Now it doesn't. I wrote rectangular just so we would know that. But understand that sometimes it's very difficult if you're not told what you're dealing with. So in this video, we're talking about going from rectangular into polar. What that means is that if we're given a rectangular coordinate representation of a point, the first thing we want to do is identify the x and the r and then plot it. Identify where the quadrant is. So x and r. X is always first, and y is always second for rectangular coordinates of a point. And so I'm going to write this out explicitly, very, very similar to what we did in the last video for r theta. We said, hey, r theta means you have a radius of 1, you have an angle that puts you in some position along the polar axis or from the polar axis, then you go out from that origin or the pole, and that gives you a specific point. Well, we always identified what the r was and what the theta was before we did any work on it. We're going to do the same thing here. Our x is 3 and our y is 0. After we do that, after we identify what x and y are, we plot our point. So x being 3 and y equals 0, because we have this rectangular coordinate system, just really handy for us, we're going to plot the point at 3, 0. Now, that's right on the x-axis. That would be like a quadrant angle, really. If we're talking polar coordinates, we're not yet, but if we were, that'd be a quadrant angle. That's right on the x-axis. So we're going to do two things. Number one thing we're going to do, the first thing we're going to do, we're going to find r. There's really never any ambiguity with r. R says just take the square root of x squared plus y squared because that is the Pythagorean theorem. If we do x squared plus y squared equals r squared, just take a square root of both sides, you get r equals x squared plus y squared. Now, you probably noticed that I'm missing something. I'm missing the negative, and that's on purpose. Really, we want to try to keep our r positive. Otherwise, we'll switch back and forth between quadrants that we don't want to be in. So we're going to take the positive r all the time. Our angle will determine our quadrant for us accurately as long as we follow this. So do your x and y, write it down, that's fine. Plot your point, identify where it is. This is somewhere between quadrant 4 and quadrant 1. Because tangent inverse is defined between quadrant 4 and quadrant 1, it will give us this angle perfectly. That's what tangent inverse does. It works perfect from here to here. That's great news. So we've done our point, we've labeled x and y, we've plotted it. We're going to find r first, and we have in the back of our mind that tangent inverse is going to work fine. So finding r. R is just a matter of taking the square root of x squared plus y squared. Because x is 3 and y is 0, that's 3 squared plus 0 squared. In our case, that's just 9. The square root of 9 is 3. Our r is 3. Now that we have our r, we move on to finding our theta, our angle. Because tangent theta equals y over x, that means that tangent inverse of y over x is going to give you theta. We already have the y and x. The y and x are your coordinates. All we've got to do is put them in a fraction in the right order and take tangent inverse. And so we're going to do that. So tangent inverse of 0 over 3. There's two things that are really important to think about. Number one, what the inverse really is, and number two, where it is. So we're thinking tangent inverse of 0 over 3, that's tangent inverse of 0. Tangent inverse of 0 is 0. So what this says is what angle gives you a y to x relationship of 0 for tangent. Sometimes having that table is really, really handy right here. So tan inverse of 0 is 0. This is an angle of 0. The second important thing to think about is where this is. So what it is, we got it. We know it's 0. But where it is. Is this angle, well, it's going to be somewhere between negative pi over 2 and pi over 2, but is it representing what we want it to? Is it representing something in the right quadrant, or at least between the same quadrants? And it is. Because our point is between quadrants 4 and 1, this angle represents this perfectly. This is an angle of 0 along the polar axis. Now, what if you had negative 3, 0? Negative 3, 0 would be over here. This angle wouldn't cut it. In that case, you'd add pi. So for anything outside of quadrants 4 or 1, just take what your tangent inverse gives you and add pi to it. It will work every time. So that's kind of nice. It's a little helpful hint. Hopefully you wrote that down. Furthermore, I want to talk just a little bit about the reason why this happens, why tangent only gives you that. You see, the problem is this: y over x. When we compare y over x, a fraction doesn't know, or a ratio doesn't know the difference between a negative y and a positive x, and a positive y and a negative x. It both works out to negative for the ratio. It also doesn't understand the difference between positive y positive x and negative y negative x. That's exactly why tangent inverse can't give you out both something in quadrants 1 and 3. Positive y positive x and negative y negative x, when you put them in a fraction, work out the same. They're both positive. That's why tangent's positive here and here, and why tangent inverse cannot give you out both. It will only give you out things in quadrant 1. The same thing happens with positive x negative y, or positive y negative x. It gives you out a negative for the fraction. Tangent inverse can't give you out both, so it only gives you out quadrant 4, and we have to understand that if our angle, if our point is somewhere between here and here, we have to add theta. We have to add pi to whatever angle we're given. So now that we have this, we know that our r is 3, our theta is 0, it's in the right quadrant, or at least between the same two quadrants. This right here would be an angle of 0 and an r of 3. It's the same exact point. It just has a different representation. And so we can write it a little bit differently. Actually, write it the same, but it means something different. We're still going to write 3, 0. The way we write polar coordinates is r comma theta, so 3, 0. And that would be the polar representation, or the polar coordinates for that point. I hope it makes sense. I hope you're seeing that it's really not a hard process. You really are just using two things, two formulas really. R is Pythagorean theorem, and to find our theta, we're using a tan inverse. We just have to be careful here. If your point is in quadrants 2 or 3, add pi to whatever angle this gives you. If your point is in quadrant 4 and you need a positive angle, add 2 pi, not pi. Even though the period of tangent is pi, we don't want to be outside of the correct quadrant, so you have to add 2 pi to get back in the right quadrant, but make it positive. Okay, we're going to move on a little bit, but we're going to go a little bit quicker since we've explained everything about it. We're just changing between rectangular coordinates and polar, x comma y and r comma theta. So whenever we're given a rectangular coordinate representation of a point, the first thing we want to do is identify the x and the y. So in our case, x equals 2 x equals 0 and y equals 2. Next thing, plot it, see where it is. Because x is 0 and y equals 2, that puts us on the y-axis, the positive y-axis. Right there at 0, 2, what we would expect. From there, we can always find r very nicely and pretty easily. There's never an ambiguity with r. All you've got to do is take the square root of x squared plus y squared, keep the positive r, because the angle will determine the correct quadrant for you. So r for the distance, r for the radius, and angle for the where it is at. In our case, because 0 squared is 0 and 2 squared is 4, the square root of 4 is 2. I keep the positive r. This is how far away from the origin, or the pole, we really are. That's great. Now we got to locate where this is to get the right orientation on the polar axis. So r first, never an ambiguity, just tells you how far you're away from the origin, and then our theta tells you where you are at in relation to your really x-axis, but we call a polar axis for polar coordinates. So now we're going to find theta. And you go, wait a minute, Leonard, you're giving me tangent inverse of 2 over 0. 2 over 0 is undefined. Yes, it is. Now think about where tangent is undefined. What angle would give you tangent of an undefined relationship? Think about it. It would be pi over 2 or negative pi over 2, or 3 pi over 2. Now, which one is appropriate? This is why I'm giving this example, so I can illustrate this concept right here. You have to think about where your point is before you pick the appropriate theta, before you pick the appropriate angle. So we have a couple choices. Tangent is undefined at pi over 2 and negative pi over 2, or pi over 2 and 3 pi over 2. Now, which one of those actually fits this? Well, let's see. 3 pi over 2 would be all the way right here. That's not where my point is. Pi over 2 would be right here. That's where my point is. Negative pi over 2 would be down here. That's not where my point is. So the only appropriate choice to have the same point with different coordinates is to pick an angle of pi over 2. Remember, our angle locates where our point is. So pi over 2 says, oh yes, pi over 2 would be right here. Oh, that's where my point is. So we plot our point, so it helps us to determine that. If we hadn't have plotted that, we very well might have looked at this and go, I don't know which to pick, negative pi over 2, pi over 2, because when we're asked for this, it says tangent inverse of 2 over 0, that's tangent inverse of an undefined thing. Tangent is undefined when our angle is what? Basically it says what angle gives you tangent being undefined. That would be pi over 2, negative pi over 2, 3 pi over 2, any multiple of pi over 2, that would be a problem. We have to find the right one that represents where that point is perfectly. The only one that does is not negative pi over 2, not 3 pi over 2, but pi over 2. It still gives us something undefined. That's still represented as well, but it's locating where that point is exactly. Now that we have that, all we got to do is put it in a point, in a polar coordinate point. So that would be r comma theta. That's r or 2 comma pi over 2. And that's exactly where this point is in polar coordinates. If I went pi over 2, that's saying this is where I'm at, go from the pole up to or along this angle 2, and you're going to be exactly right there. It's representing the same point in a slightly different look. Okay, next one. We have a point in rectangular coordinates that's 1 comma negative 1. The first thing we're going to do to convert to polar is make sure we understand what the x is, what the y is. I always write it down to make sure that I don't accidentally change things, especially when finding my angle. Hopefully you understand why that's so important. If I plot this incorrectly or find my angle incorrectly, have that thought down, I'm going to get a completely wrong quadrant. I don't want to do that. So I'm going to label this as x, y. Make sure my x is 1, my y is negative 1. So once I've done that, I want to make sure that I plot this point before I do anything else, even find r. Even though it's a little bit easy, what I want to do is make sure that we plot this to locate where it is. So because x is 1 and y is negative 1, that's going to put us squarely in quadrant number 4. So our point is 1, negative 1. I'm going to think, hey, this is in quadrant 4, but I do have it written down, so I can always look back at my graph and say, hey, I plotted this point. It's in quadrant 4. Fantastic. That's why we do that, so we can immediately locate where this thing is. We know things about quadrant 4. We know that tangent inverse gives us out angles in quadrant 4 and 1. This is good news. That means that I'm not going to have to add pi to this because tangent inverse works well in the quadrant where my point is. That's important. So I have that in the back of my mind. So I've looked at it, said x and y are these. I've plotted it. I know where it is. Now we're going to find r. There's never an ambiguity with r. It's kind of the easy one. We're going to take positive r, saying how far we are away from the pole or the origin. The angle is where we are. And so it's a little bit more difficult because of tangent. We saw that here. Tangent inverse make things a little bit trickier because you have to think about exactly what angle to take in some situations like we already saw. So finding r though, not too bad. So in our case, r is square root of 2. Leave it as a square root. That's just fine. You don't need to put 1.41 or anything unless you absolutely have to approximate it. Leave it exact. We really don't want to lose exactness here. We're trying to represent exactly where this point is in a different type of coordinate system. So this is exactly where this point is in terms of x and y. We're finding exactly where this point is, and we already had this in terms of r. Now we just need to find theta. How do we find theta? Well, we do tan inverse of y over x, and we really want to make sure we get that as y over x. That's why we label it. So we go, okay, y is this, x is this. Now we think about that. So tangent inverse of -1. What in the world is tangent inverse of -1? Tangent inverse only gives you out angles from -pi/2 to pi/2. So tangent inverse of -1 says, what angle will give me a y over x of -1? That's going to be -pi/4. That's how tangent inverse works. Remember, it gives you from -pi/2 to pi/2. So yes, it works in quadrants 4 and 1, but it will only give you out negative angles for quadrant 4. That's going to lead us to a note here in just a second. So our theta is -pi/4. Now, you're done. Tangent inverse works great for points in quadrants 4 and 1. Since our point is in 4 and 1, tangent inverse gives us out angles in those two quadrants. That's perfect. We could easily write this as r comma theta, or square root 2 comma -pi/4. Now, I did say there was one caveat for points in quadrant 4. We're going to write a note here. If you have to have a positive angle, so it says, give me your polar coordinates, but I want you to make sure that you're from 0 to 2 pi. This is not in it. This is below 0. And so that would be a problem. If you have to have positive angles and you have a point in quadrant 4, tangent inverse will only give you out negative angles for that. It will not give you out positive. Add 2 pi. Do not add pi. Why? Why not? Even though the period for tangent is pi, adding pi would put you in quadrant 2. Hey, that's the way we're going to get angles for quadrant 2. Find this one, add pi. That's perfect. Just like if we have a point here, we're going to find quadrant 1 angles and add pi. But if I add pi to something here, it's going to give me something in quadrant 2. I don't want that. I want to add 2 pi to get back to exactly where I'm at. Oh man, I hope you remember that. If we add 2 pi, we get right back to where our point is. We've just gone one full revolution around our unit circle. That's basically the same idea. If I add 2 pi, I'm going to get right back to where this point is, but I will have a positive angle instead of a negative angle, something between 0 and 2 pi. So write a little note here. If your point is in quadrant 4 and you need positive angles, add 2 pi. For points in quadrant 4, add 2 pi. Not pi, even though the period tangent is pi. Add 2 pi to get in the same quadrant with a positive angle. So for us, that means if we add 2 pi to -pi/4, let's see, -pi/4 plus 8pi/4, that would be 2 pi, would be 7pi/4. We could write this equivalently as square root of 2 comma 7pi/4. And that would give us an r and a theta. Same exact point, whether we do this or this or this, but it does depend on how we want to see it on what we're working with. Is it the same? Does it do the same thing? Yeah, if we do -pi/4, that's that angle. That's -pi/4 and an r of square root 2. Hey, look at that. If you have a 1 and a 1 on a triangle, like an isosceles right triangle, your radius there, your hypotenuse, is the square root of 2. That's exactly why we got the square root of 2. It's Pythagorean theorem. This angle is -pi/4. Or 7pi/4. But either way, you're going to get exactly the same point with a different type of coordinate system. I hope it's making sense. I hope you're seeing why we're using these two things to get from rectangular to polar because it relates x and y to r, because it relates x and y to theta. I hope you're seeing the issue that we have with tangent inverse, that because it only gives you out angles in quadrants 4 or 1, negative pi over 2 to pi over 2, there's a little bit more work to do. That's why I said it's a little bit harder in the last video, and it is. You do have to think about it. You don't have to think about r. Keep the positive r. The angle is going to tell you where you are. So r, how far away you are. Angle, where you are, locates where you are. So we're going to talk about what happens when we don't have an angle in quadrants 4 or 1. We already talked about some quadrant angles here, which was kind of nice, but we'll go ahead and deal with angles that end up in quadrants 2 or 3 next. Let's keep right on going. So we've got a couple more points represented as rectangular coordinates. We want to translate them into polar. We're going to consider negative 3, 3. If that's rectangular, which I've said it is, then x is negative 3 and y is positive 3. We're going to write that down first. After that, we're going to plot it, and we're going to start thinking about where that's at. Negative 3, 3 puts us into quadrant 2. Right about there. Now, another thing, these don't have to be perfect. You just really have to get the right quadrant. So whether or not this is to scale or anything, especially on stuff like negative 2 square root 3, who cares? It doesn't really matter. What matters is a representation telling you where the quadrant is. Why? Because in the back of my head right now, I'm thinking r is going to be nice to find. It's never going to be ambiguous for us. But when I go to find my angle, tangent inverse can only give me out angles in quadrants 4 and 1, negative pi over 2 to pi over 2. In fact, in quadrant 4, it only gives negative angles. So I have to do something with those angles if I need a positive. But for angles in quadrant 2 and 3, I'm certainly going to have to add pi to whatever angle I find here. So I have that in the back of my head. So I've thought x, y, I've plotted it, I know my quadrant, I'm in quadrant 2, I'm thinking about angle ahead of time. Now I'm going to find my r. And it looks like our r is 3 square root 2. So negative 3 squared is 9, 3 squared is 9, 9 plus 9 is 18. The square root of 18 we can simplify by taking that and factoring that is 9 times 2. The square root of 9 is 3. Square root of 2 is, I don't know, the square root of 2. But we do have the first half of our polar coordinates. We have 3 square root 2. Now it's time to find theta. Theta is still found by using tangent inverse and relating y over x. That's fine. But what we do is we realize that because the angle it's given us is not in the right quadrant, we have to do something to it. And you can probably see it here. Tangent has no way of telling whether you mean negative 3 over positive 3 or positive 3 over negative 3 because of the way that negatives work in fractions. We explained a little while ago, but there's no way for it to know, which is why we had to choose when we define tangent inverse to only pick quadrants 4 and 1 because of the one-to-one function inverses have to be. Otherwise, we'd have 2 options every time, and tangent will let you do that. So because tangent inverse only gives you out angles in quadrants 4 and 1, this right here, this tan inverse of negative 1, is going to give you negative pi over 4 again. Now, really appreciate this. Please don't just treat this as like a formula. Please don't treat it like, oh, if it's in quadrant 2, I just add pi. You can, but really think about why that is. Tangent inverse gave you this angle of negative pi over 4. From your polar axis, that's going to be here. They would say, here's where your point is. But that's not right. My point is in quadrant 2. How do I get to quadrant 2? Add pi. That's why this works, is because this is always going to be off 1 pi away from your actual quadrant if your points are in quadrants 2 or 3. It's going to give you something that's pi radians away. So this says, all right, negative pi over 4, that's the wrong quadrant. I'm going to add pi. It'll put me into quadrant 2. So let's see, negative pi over 4 plus 4 pi over 4, that's 3 pi over 4. Can you see how a lot of people who really don't understand what tangent inverse does, they would give that. And then they'd be really confused, like, why doesn't that work? I'm doing tangent inverse, it's what the notes say. It does say that. But because of the way tangent inverse works, we have to really think about what it's giving you. And if we're outside of what it's giving you, you just add pi to it because it'll put you in the correct quadrant because it can't give you out everything. It only gives you out half the unit circle. So that's why that's a no-go. You do not want that. And sure enough, when we do plot the polar coordinates with an r of 3 square root 2 and a theta of 3 pi over 4, r tells you how far away from the origin or the pole you are if you superimpose a polar coordinate system on this. That would act as your origin or the pole. The theta tells you where you are. So 3 pi over 4 says from your polar axis, basically the x-axis, your 1, 2, 3 pi over 4, and your whatever that r is away. That's exactly the same point in exactly the same location. We didn't approximate anything about this. That's perfect. That's what we're looking for. It matches the right quadrant. That's really what we're checking here. If our math is right, which it is, then we've just represented that point two different ways in two different coordinate systems. Let's move on to the next one. So we got another rectangular representation of a point. We got -2 comma -2 square root 3. First thing we're going to do, identify x, identify y. Second thing, plot it so we can identify the quadrant. So -2, x is -2, comma -2 square root 3, y is -2 square root 3. That's going to put us into quadrant number 3. Now you notice that I don't really know exactly where that is, -2 square root 3. I don't really care. As long as my quadrant's correct, it's going to be just fine for us. Our angle might be a little funny for our polar coordinates, but that doesn't really matter as long as our quadrant is right. So I've represented this as -2 square root 3. It's in quadrant number 3. So in my head, what am I thinking? I'm thinking r is going to be fine. We're going to take the positive r like we do all the time. Just tells us how far away we are. The angle is going to tell us where we are. But because I'm in quadrant 3, I know that what I get from tangent inverse is not going to be the angle I need. It's going to be pi radians away. I'm going to be adding pi to this because this angle is going to give us something out in, or this point, this tan inverse for this point is going to give us something out in quadrant 1. I'm going to have to add pi to it to get quadrant 3. So with our r, we're going to take -2 squared plus -2 square root 3 squared, all inside of a square root. That's going to give us 4. This is going to give us 4 times 3, which is 12. So 4 plus 4 times 3, that's going to be 16. That's square root of 16. So we know for sure that for our polar coordinates for this point, r is 4. We're going to be 4 units away from the origin, or 4 units away from the pole. That's great news. Now we're going to focus on our theta. So theta equals tan inverse of y over x. What happens when you take -2 and divide by -2? What do you get? You get positive. You get positive 1 times square root 3. This is the last time I'll say it, really. This is why tangent inverse can't give you both. It can't tell the difference between negative and positive. And so it chooses to take the positive, quadrant 1, rather than quadrant 3, so that we had a one-to-one function for tangent so that it would actually become an inverse how we wanted it to. And so this right here is going to give you out an angle in quadrant 1. So this says, all right, what angle gives you a y over x relationship or ratio of square root 3 over 1? I'd use my table. It would be just fine. What we're going to get out of that, let's see. Sine has to be bigger than cosine. So it's got to be square root 3 over 2 over 1 half. That's got to be pi over 3. So I know that theta here is pi over 3. Let's put pi over 3 there for a second. Is that going to work? Well, we can try. Here's pi over 3. Boop. That doesn't look like where my point is at all. If I go pi over 3 and up 4 along that angle, that would be incorrect because that is not at all the right quadrant that I want to be in. Now, some of you are thinking, well, wait a minute. What if I did pi over 3 and did a negative 4, negative r? That actually would work. But because we prefer positive r, we really like to keep r positive and angle where it actually is in the correct quadrant. That's a little bit less confusing to see. But it is possible to do this with a pi over 3 and a negative r reversing your quadrant. That's a little bit of tricky math, but you could do it. So I don't want the pi over 3. What I want is the angle that puts me in the right quadrant with the positive r that I've already chosen. So in order to do that, if my pi over 3 says I'm here, I'm going to add pi to get into the correct quadrant. So pi over 3 plus 3 pi over 3, that's the same thing as pi. That's 4 pi over 3. And what we'd end up with is 4 comma 4 pi over 3 in terms of polar coordinates. Let's see if that works. 4 pi over 3 would be, let's see, 1, 2, 3, 4 pi over 3, and out 4 units from the origin or the pole. That's going to put us in exactly the same position as our rectangular representation of that point. It is the same. As long as we identify the quadrant our point's in and let tangent inverse give us out the right angle for 4 and 1, add pi. If you're in 2 or 3, you're going to be all set. If you need positive angles and you have a point in quadrant 4, you have to add 2 pi. So I'm going to come back with some awkward ones. The things that aren't on your unit circle, we'll talk about how to deal with that. Okay, so these look a little funny because those are decimals and we haven't really dealt with that before. We dealt with some square roots, which worked out very nicely, things on a unit circle, and these are not. So I wanted to give you 2 examples on how to deal with that. Thankfully, the techniques that I give you typically work all of the time. Always work all the time because I don't like teaching 2 different things. So this is why that I gave you draw the picture and plot your point, because it will determine whether or not to add pi or not, or add 2 pi if you have quadrant 4 and you need a positive angle. So that's why I gave it to you. And so we're going to follow the same exact steps. The only difference is that you're not going to be able to find an exact representation of your angle on a unit circle. You'll have to use a calculator and we'll approximate that, and that'll be just fine. So the first thing, hey, we got a rectangular coordinate representation of a point. Let's write down x, let's write down y, let's plot where that is. So positive 1.3 for x, negative 2.1 for y puts us into quadrant 4. Let's say right about there. All that really matters is that we are in quadrant 4. That's how we're going to find our theta in just a moment. So now that we've plotted that, we know we're in quadrant 4. I'm thinking in my head, this is going to give me out a negative angle. I hope you see that. Tangent inverse is going to give me out a negative angle for quadrant 4. If I need a positive, I'm going to have to add 2 pi. I'm not going to add pi. I want to stay in quadrant 4, but I would add 2 pi. Tangent inverse gives you out things in 4 and 1, but negatives in 4. Let's find r first. So with r, we're going to take a square root of x squared plus y squared and you get square root of 6.1. This is exactly what r is. I didn't round that at all. So if you wanted an exact approximation or exact representation of r, it would be square root of 6.1. If you're okay with an approximation, this is about 2.47. So you could use square root of 6.1 there, or if you're approximating 2.47. That's the distance away from the origin that this point is. All we need to know is the location of as far as an angle. So what angle it creates with our x-axis or polar axis. In order to find that, we're going to use tan inverse. Now that's not super nice because we can't really simplify it, and it's not on our unit circle, and so we're going to have to use our calculator. And so what we do is we just press tan inverse, make sure that you are in radians. Please make sure you're in radians if you're going to represent this in radians, or degrees if you're representing degrees. Most of the time we pick radians and we add pi as 3.14 or 2 pi as 2 times 3.14 to make sure that we're in the right location for our quadrants. So I'm going to make sure that my calculator is in radians. That's about negative 1.02 radians. What in the world does that mean? Remember what pi is. Pi is approximately 3.14 radians. So to get from here to here would be 3.14 radians. 1 radian is really what 1 radian was the angle it took to create a radius equal to the arc length, where it's 1 and 1. That's really what it was. And so our run radians about right there. It takes about 3.14 to get to pi, exactly about 3.14 to get to pi. So negative 1.02 radians is, well, where would it be? It wouldn't be past quadrant 4 yet. It'd be somewhere between here and here. Why? Because pi over 2, 3.14 divided by 2, is more than 1.02. So negative pi over 2 is more negative than negative 1.02. That angle is somewhere in here. That's great. That's what we wanted. That is in quadrant 4. So if that's acceptable, if you have negative angles, you write that down and you're done. What if it's not okay? Well, if we found anything out, it's that tangent inverse only gives you out negative angles for quadrant 4 and only angles from 4 to 1. So if you need to keep your angle in quadrant 4, but you need it positive, you have to add 2 pi. Well, now what is 2 pi? 2 pi is 2 pi radians. That would be 2 times about 3.14 or 6.28. So if we add 2 pi to this, we get approximately 5.26 radians. What in the world does that mean? That means this. You can locate the same exact point with an r of around 2.47 or exactly square root of 6.1 and either negative 1.02 radians or positive 5.26 radians. Think about this. 5.26 radians is less than 2 pi radians. It's just 1.02 radians less than that. It's going to give you the same exact location at that point. So whether we go negative 1.02 or positive 5.26, we still do end up in quadrant 4. That's exactly what our point told us we needed to do. That's exactly where our point is, just a different representation. I hope that one makes sense. That gets a little wild if you don't have a picture of that. You go, I don't even, what does negative 1.02 even mean? That's what it means. I hope I've explained it well enough for you to understand it. Let's go on to the next one. So we have one last rectangular representation of a point. Our x is negative 0.8, our y is negative 2.1. We're going to write that first. Then we're going to locate it. So negative, negative says we are in quadrant 3. Somewhere about right there. So negative 0.8, negative 2.1. At least we know we're in quadrant 3. Now that says something about our theta. When we get tangent inverse, it's going to give us something in quadrant 1. We're going to have to add pi to it. Let's find our r first, but we have that in the back of our head. And if we do all the work on that, if we take x squared plus y squared, take a square root, we'll have square root of exactly 5.05. So that is an exact answer. If you needed exactness, you would use this one. An approximation is, I took a square root, I got about 2.25. So our r right now, our distance from the origin is approximately 2.25 units, or exactly square root of 5.05. And then we work on theta. Because theta is given by tan inverse, all we're going to do is take our y over x, but that's not a unit circle. Negative over negative gives us a positive. It's going to be in quadrant 1. Tan inverse, when using our calculator, is going to give us about 1.21. About 1.21 radians. Now, is that okay? Is that where we want to be? Because 1.21, well, that's not really even to pi over 2 yet. So we are about right there. That's where 1.21 radians is. If we go to 1.21 radians and we go out 2.25, we are the right distance away from our pole, but in the wrong location. We're in the wrong quadrant. Tangent inverse cannot give you anything in these two quadrants. I've made that very clear. So what do you do to get to this quadrant? You have to add pi to it. Because pi is approximately 3.14, we can do that. Add approximately 3.14 will typically work. Most calculators have a pi button on there, so we're going to add pi for anything that's in quadrants 2 or 3. Add pi to the angle that you get, you will be fine. You can even most of the time subtract pi, but you'll get negative angles. So you can add pi to anything in these two quadrants. Add pi to the angle you get, you'll be perfect. Anything in quadrant 4, add 2 pi to if you need a positive angle. So I'm going to add pi because I was in quadrant 3. The angle says I'm in quadrant 1. Pi will take care of that. And so if we do add pi and round it appropriately, we're going to get 4.35 radians. Let's see if that makes sense. 3.14 radians puts us about at pi. Pi is a little bit more than that, but 3.14 radians would be here. 4.35 would be past that. Hey, we're in the right quadrant. It's not yet to 3 pi over 2. That's not enough. So we are all the way to here. And out 2.25. That's exactly the same location at that point with a different representation. I really hope I've made it clear on how this works. The r is pretty straightforward. We do generally keep the positive. I gave you one instance where you could take the negative and still get the same location, but it is more difficult to see. For that reason, we almost always take the positive r here. We let the r determine the distance from our origin or pole. We let the theta determine our location. For quadrants 4 and 1, you have the right angle from your tan inverse. For quadrant 4, add 2 pi if you need positive. For points in quadrants 2 and 3, just add pi to the angle that you get. That's about all there is to it. Next time we're going to talk about is how to convert equations from rectangular to polar, and then a different video on polar to rectangular. Hope you're doing well.